So I'd like to give you a quick introduction to advancing the search for dark energy with Parsl and high performance computing. So I'm Tom Glanzman. I'm at the SLAC National Accelerator Laboratory. And this work was done in close collaboration with Ben Clifford, who really adapted an existing desk workflow to Parsl initially and continues to partner in this endeavor. So a quick introduction to the projects themselves, the Rubin and desk projects. The Vera Rubin Observatory, formerly known as LSST, is a joint Department of Energy and National Science Foundation project. It's an astronomical observatory, will be sited on a mountaintop in Chile. It has a large 8.3 meter diameter primary mirror, a very wide field of view. It will contain the world's largest digital camera, 3.2 gigapixels. It's expected to begin operation in a couple of years and run with a 10-year whole sky survey program. So what is dark energy? That's one of the questions that is that comes up a lot and is a little bit tricky to answer, but I found a pretty concise quote here. Dark energy is the name given to the mysterious force that's causing the rate of expansion of our universe to accelerate over time rather than to slow down. So that's basically what the Dark Energy Science Collaboration is studying. The collaboration itself was started about 8 years ago. It now has over 1,000 scientist collaborators, and the plan is to exploit the Rubin data to study clues to dark energy. A couple of pretty pictures. Upper left, there's the picture of the observatory as it was a couple of weeks ago. The building exists. On the right is a picture of the telescope mount assembly. It was still in Spain at that time where it's been fabricated. And then the final picture down in the lower part is actually a picture of the large 8.3 mirror being ground in Tucson, Arizona at their mirror factory there. That's quite an amazing process. And then finally, the camera itself is consists of 189 science sensors, each of which are 4K by 4K pixels. There are 12 special purpose sensors in the corners. And what you see there at the top is the final raft of sensors being installed earlier this year. And then finally, there's an image there, a pinhole camera image of Vera Rubin herself that was actually taken by this camera. So it exists, and it's in the process of being finished the assembly and testing. Okay, so the observatory isn't built yet. It's in the process of being built. We won't have data for another couple of years, but we must hit the ground running. So therefore, we have a number of data challenges that have been set up by the collaboration. And this basically means simulating part of the sky, exercising all of the standard software that the Rubin project is developing to process the data and make catalogs of astronomical objects out the other end. And we want to develop the desk-specific algorithms and test those on these resultant catalogs. So we have a series of data challenges. We're now in the middle of what's called Data Challenge 2. There was a Data Challenge 1. And this is to simulate a part of the sky, fairly small part of the entire sky, but it's 300 square degrees, and to cover about 5 years of the Rubin survey program. So a much simplified diagram of the computational steps involved in this data challenge are we need to generate a simulated catalog of objects. Then we need to simulate the images. These would be comparable to what we would read out of the, what we would acquire out of the telescope itself. Then there's the image processing. What do you do with the raw data? You generate, what comes out of that are astronomical object catalogs. And then finally, there is what I did not put at the end is all of the analysis. So there's very natural parallelization in this. There are many, many images taken over the course of this 5-year data challenge. The instrument itself is composed of many individual sensors, and the processing can be done in parallel over different patches of the sky and so forth. So it's relatively straightforward to apply kind of standard parallelization techniques. The data challenge itself generates a fair amount of data. It'll be over a petabyte, and it will consume tens of millions of CPU hours. So DOE has provided cycles for us to use at NERSC and at Argonne. And I might mention that the image simulation step was actually managed by Parsl and presented last year at the Parsl Fest. So Parsl at NERSC. To remind people who may not be familiar with NERSC, it's a large high-performance computer. The main part of that machine we call Cori KNL, KNL for the Knights Landing chips that are used in this machine. There are about 10,000 nodes. Each node has 68 cores. Each core has 4 hardware threads. It's a fairly modest clock speed, 1.4 gigahertz. So it's not the speediest chips in the world. And there's 96 gigabytes of memory per node. The storage is a combination of GPFS and Lustre. Batch access is via Slurm. So what does that mean for us? The challenges are that there's relatively little memory per core or per hyperthread, so about 1.5 gigabytes per core. Disk I/O can be problematic, slow, or even erratic. So we've had to deal with a number of problems in the past with disk I/O. The Slurm queue often experiences very large dispatch latencies, anywhere from hours to days, depending on what you're asking for. So even small jobs, there can be a problem just waiting for tests to complete. And of course, it's also a problem for production throughput. And also, I just wanted to note here that the Rubin LSST codes are manifestly single-threaded. They were not designed to take advantage of a high-performance computer. So you can see that right off the bat, this is not the ideal match of a program environment and our problem that we need to solve. So let me just show you something about, this is all I'm going to show you about the Parsl data flow itself. The processing is fairly straightforward. It's a sequence of steps. These steps are Python and C++, and they represent the processing all the way from raw camera images to catalogs of sky objects. And for this particular workflow that we're working on right now, I've listed the various Parsl apps used in the workflow. And I'd just like to point out a couple of things about this. In the column called instances, that indicates our current estimate of how many instances of this task are going to have to run to satisfy this data challenge. And then I've also indicated on here that we're using a number of different high throughput executors to try to better match tasks to needed resources. So the kinds of things we're doing is we need to worry about what the memory footprint is of each of these tasks. And the memory footprint can vary quite a bit, even within a given task, because as you look at different regions of the sky, you'll see different populations of objects. And this can increase or decrease your memory footprint. And that also applies to the amount of time it takes to complete one of these tasks. So what we've done is we've tried to characterize these different processing steps and make an estimate of what kind of executor configuration we need to make everybody happy. So as you can see, there are some kinds of tasks which we can run a large number on a given Cori node, and they don't take much time and they don't have a very large memory footprint. On the other hand, there are a number of tasks that have a larger memory footprint or take a great deal more time to execute. So this is our current scheme. And we are on the cusp of actually a very large production. NERSC is having a little bit of a technical problem right now, but once that gets cleared up, we expect to be embarking on this production. So let me change gears just a little bit. Oops, hang on.
Just note, Tom, we're probably a minute or so to go.
Okay. Let me just say something about monitoring. So there is Parsl now has a monitoring feature, and a little script has been developed to try and interrogate that monitoring database and summarize the data inside of it. And this has been very useful for very large data flows because you really want to have your finger on the pulse of what's going on. One of the things it does is it can also pull out the runtime and produce some execution timing. And there are a lot of other kinds of reports that it does. And I put some of these in the backup slides in case anybody is interested. So let me just finish with one last slide. This is my personal Parsl wish list. There are a number of things here that have come up over the period of this work. So one item is the ability to kind of roll back a selected task within workflow. I won't go into too much detail as to the whys, but they're listed here. The Parsl developers may find this more interesting. An improved executor or executor to better control over task assignment to batch nodes. For example, don't start a task that you think is going to require 3 hours on a batch node that only has 1 hour remaining. Similarly, don't start a task with 4 gigabytes of memory on a node that only has 1 gigabyte remaining. And there are other kinds of resources that would be useful to consider here too. And the flexibility to request the number of nodes for a given job according to the task backlog. And maybe that's something that's already being handled by Parsl a bit. But with the monitoring, I'd like to see the monitoring extended to the remaining executors. It's difficult to collect performance statistics without that. To make the monitoring data reliable, there are cases where the data are lost. Better accounting of batch jobs. For example, when does a batch job start? When does it end? And some record of how many workers are running on that batch job at any given time. Some of these I've actually already submitted GitHub issues on. Another is to record task failure codes so we can more easily kind of harvest those and figure out if there are some systemic problems happening. Command and control with the communication with the running workflow. For example, if you want to modify the configuration of an executor while your workflow is running because of changing conditions, it would be useful to be able to do that without having to kill the workflow, edit your configuration and restart it. Support for application level checkpointing. This is mostly I would say a bookkeeping exercise, but there are things that could be done that would make it a lot easier to use tools such as, say, DMTCP. Okay, so I will stop here. There are some backup slides, which I'll make sure that Kyle gets and he can put up on the web in case anybody is interested. Thank you very much.
Wonderful. Thank you, Tom. Time for one quick question. I should also say Tom undersold the monitoring scripts that were developed. Tom developed a lot of that software himself, and I think it's really quite useful. So if people are looking for a way to monitor Parsl workflows from their CLI, from their shell terminal, yeah, get in touch with us and we can get you Tom's tools. Okay, well, quick question.
That was my question, Kyle. I mean, the WStat just looks really, really awesome, Tom. First off, thanks for that amazing talk. I really enjoyed it. So what are your plans as far as, I mean, could we make WStat more, I mean, we need to get it to the people. It looks very, very useful. Do you have any plans for that?
So a couple of comments. One is that it's really a work in progress. As my experience grows using Parsl in this particular application, I'm continually saying, gosh, I'd really like to be able to see these statistics, and then I have to learn how to go and pull them out, and then Ben comes along and pulls the rug out from under me and changes, what's in the monitoring database. So I have to refigure out the appropriate queries and so forth. So at any given moment of time, there may be things that are working and not working. So it's not really production status at the moment, but it could be helpful to people who are just getting started or who have a workflow that's a little bit on the large side and they just want to see what's happening. So it's in a GitHub repository, and I'm happy to, if people want to take it out for a spin, that would be just fine. I intended it to be kind of a general purpose tool. It's not tied to this application at all, but it's by no means complete, and there are probably bugs in it.
Well, perfect is the enemy of good enough. I mean, I think a lot of people would be excited to take it on a spin. So I encourage you to post that link on your slides and people could check it out.
Yeah, I think it's a great thing as well that we can have students and others contribute to. I think it's the sort of code that people can really adopt and improve over time. So,
but we're not trying to create work for you, Tom. So we're not, we know that, we know that the reasons for being cautious there, but it does look very, very useful. So I'm excited to check it out.